So we just finished one section, a general introduction of sets and the subsets and the operations of sets. You can do different things on the sets. You can do the intersection, you can do union, you can do subtraction and complement. So one of the things to be cautious, when we talk about the sets, is a set can be an element of another set. And especially for the empty set, it does not have element in itself, but it can be an element of another set. And that is counted as something. So if another set has the empty set as an element, then that set is not empty. All right. Sometimes it makes a lot of confusion when we talk about the relations between the sets and subsets. Just be careful to understand completely the definition. You just think an empty set as an empty box. So if the set is not empty, then the box has something in it. But for the empty set, it's just a box. But it's not nothing, okay? The empty set itself is a box. So that is something. And we talk about the power set, remember? That's the collection of all the subsets of a given set. If you put all the subsets of a given set in one set, that set is called the power set of the original set. Okay, so the elements of a power set is the subsets of another set. All right. So it includes a lot of definitions. I know you learned this before, but you probably need to refresh or review a little bit, because sometimes the situation could be tricky. So let's just start a new section today, section 2 of chapter 1 or unit 1. Products of sets and the index sets. Okay, so this is a different thing. So we can do different operations with the sets, and in addition to the union, intersection or complement or subtraction, we can also multiply two sets. Okay, and that's called the product of sets. And this product of sets is extensively used in all areas of mathematics, and of course in groups. So let's just start from the Cartesian products. So suppose you have two sets, then you can form the Cartesian products of those two sets, just like you do the numbers. But the meaning is totally different. So how do you multiply two sets? And the Cartesian product of two sets gives a new set. And the element of the new set comes from both sets with ordered pairs. All right, and elements or numbers in the ordered pairs coming from the two sets individually. And that's the ordered pair. So this is the set of all ordered pairs such that the first entry comes from S and the secondary entry comes from T. So if you write S cross T, it means the ordered pairs of ST where the first entry of the ordered pair is from the first set, and the second entry or coordinate comes from the second set. And that's how we define the XY plane actually. If you think the ordered pairs gives you the coordinates of points. And this Cartesian product actually gives you a plane. We have the X and the Y axis. So you can pick up all real numbers on the X axis and call it S. Okay. And you can also pick up all numbers from another real set, the set of real numbers, and use those numbers as the second coordinate in the ordered pair, and we call it the coordinates. So in that case, we can write R cross R equals R2, all right? And we will often refer to S cross T just as the product of S and T, as we just read in here. So because the pairs in the Cartesian product of the sets is ordered or ordered, if you switch the order of S and T, you're going to get a different Cartesian product. Okay. Usually S and T are different. So if you write T cross S, then the element in T will comes first in the ordered pair, and the elements in set S goes to the second place in the ordered pairs. So that will give you a different new set. So let's just do some simple examples. So suppose we have two sets S and T. Set S has 3 elements, and set T has 2 elements or 2 numbers. 1 to 3 in S and 1, 2 in T. By the way, we should be careful when we talk about elements of a set and subsets of a set. We use belongs to when we talk about the elements in a set or of a set, and we use contained when we refer to subsets of a set, and we have different notations for those two relations. And we actually talk about the proper subset, if the subset is not equal to the original set, it's called a proper subset. And we have also some subtle notations for those. Anyway, So let's see what is cross T and what is T cross S. So first, we have all the pairs coming from S and T. In the first place, when S cross T, then you put the elements or numbers of S first, and the numbers of T secondly in all the pair. So we have three elements in S. So if you just list each of those elements starting from 1. So if you pick the element 1 in S, then you will have two choices in the place of the second place of the other pair, which are 1 and 2 from T. So then we have two other pairs from the first element in S. So that'd be 1, 1, and 1, 2. Now, if you pick up 2 from the set S and put in the first place of the other pair, then again, you will have two choices to pick numbers from T and put them in the second place in the other pair. So that will give you 2, 1, 2, 2. And finally, you can pick up 3 from S and put in this first place of the other pairs. And then you have two choices of numbers from T going to the second place of the other pair. So that will be 3, 1, 3, 2. And that's all. So how many elements? 1, 2, 3, 4, 5, 6. So there are 6 elements in S cross T. And if you use those other pairs, or plot those other pairs in the XY plane, that will be 6 points. Okay, so 1, 1 in here, 1, 2 here, and what else? 2, 1, 1, 2. Oh, 1, 2 goes up. I'm sorry. So and 2, 1 in here, 2, 2 goes up, 3, 1 go to the right, 3 to go up again. So we got 6 points, from S cross T, like this. How about T cross S? So this time you can pick up elements or numbers from T put in the first place of the other pair. So if you pick up 1 from set T, the first set in the product, then you will have 3 choices of numbers from S, 1, 2, 3. So that will give us 3 other pairs, 1, 1, 1, 2, 1, 3. So so that's when you pick up 1 from T, but you can also pick up 2 from T. So then for each of, for these 2, you can pick up 3 numbers from S and put in second place. So that will give you 2, 1, 2, 2, 2, 3. So again, we got the 1, 2, 3, 4, 5, 6 elements in this quotation product. But just be careful, this T cross S and S cross T, if you compare the other pairs, they're not the same. For example, in T cross S, we have other pair of 1, 3, but that's not in S cross T, and so on. So if we plot those 6 points on the XY plane for T cross S, and then they will have, 1 as the X coordinate and the 1, 2, 3 as Y coordinate. So it goes up from 1, 1, 2, 3. And then you pick 2 for X, and Y changes from 1 to 2 to 3. So you get another 3 points going up from 2. So you got some different points between those two products. All right, if you plot them. Okay, so I didn't show it here, but that's easily done. That's easily to figure out. So you can see from both Cartesian products, although they are not the same, they do have the same number of ordered pairs. Each has six ordered pairs, and that's not accidental. Okay, actually, if you use the notation for cardinality, so then the cardinality of S cross T is just 6, and if you remember the cardinality of S is 3 and cardinality of T is 2, so you multiply 3 by 2, you get 6. And that's actually a rule. Okay, so that's summarized or generalized in the proposition. It says let A and B be finite sets. Okay, so each set has a finite number of numbers or elements with the cardinality of A equal to M and the cardinality of B equal to N, then A cross B is a finite set also with the cardinality of the product of A B equals M times N. Just multiply the cardinality of each set. Okay. Any questions about this example? Pretty simple. I apologize for this shading, by the graph for some words. So that's the product of two sets. If no question, let's just go on to the next page. Okay, let's see more examples. So this time we have a different situation. The two sets A is actually, set A is the set of all natural numbers. So it's infinite set. And set B is finite. It just has two elements or two numbers, 0 and 1. So if you form the product of A and B, A cross B, then you put B, the elements or numbers in B in the second place, and put the numbers in set A in the first place, as we know. So you can list some of those ordered pairs in A cross B. For example, if you pick 1 from set A, then you have two choices from B. So that'll give you two ordered pairs, 1, 0 and 1, 1. And that's all for for the number 1 in set A. Now, if you change the number to 2 from set A, then again you can choose 0, 1 in the second place of the ordered pair from B. So you get 2, 0, 2, 1. And if you choose 3 from the first set, then you have 3, 0, 3, 1, and so on. So if you plot those points, so 1, 0 is on the x-axis, 1, 1 just go up 1 unit, 2, 0 on the x-axis again, then 2, 1 goes up 1 unit, another point, 3, 0, 3, 1, 4, 0, 4, 1, 5, 1, and so on. So you got an infinite number of points. There are, half of them on the x-axis and half of them on the horizontal line, y equal to 1. Okay. So you can use short notation for this Cartesian product of A and B. So for each of number n you pick up from set A, you only have two choices for the second place in order pair from B, namely 0 and 1. So you have n0 and n1, so 2 points for each number in the first set A. And then you just choose or pick all natural numbers in the place of first place of the other pair. All right, so that's A cross B. If you do B cross A, then this time you can only have two choices in the first place of the ordered pairs, namely 0 and 1 from set B. So if you do that, you're going to get 0, 1, and 0 and 1, 1 for the number 1 in the set A. All right, and then if you choose 2 from the set A, then you also have 2 other pairs. You need to put 0 and 1 in the first place of the other pairs, and put 2s in the second place of the other pairs. So you get 0, 2, 1, 2. Similarly, if you pick 3 from set A and put in the second place of the ordered pairs, and put 0, 1 in the first place of all the pairs, so you get 0, 3, 1, 3, and so on. So again, you get an infinite number of points for all the pairs for this product. If you plot those points on the xy plane, you also get an infinite number of points. So 0, 1, so that'll be on the y-axis. 1, 1, so that's going right one place, 1 unit. 0, 2, going up on the y-axis, 1 unit. 1, 2, going right 1 unit. And 0, 3, 1, 3, so going up. So this time the points are on the y-axis, half of them on the y-axis and half of them on the line of x equal to 1. So they change to different places, those points. And you can write these points in a short notation by 0n and 1n. Okay. So we only have two choices for B, but they're in the first place. So that'll be 0 and 1 in the first place in all the pairs, and n in the second place of all the pairs. And this n can be any rational number. All right. So that's the case when you take the Cartesian product of an infinite set and a finite set. You can also do that. So in the graph, we just show the first product, A cross B, or N cross the set of 0, 1. All right, you can easily plot the points of B cross A. All right, so that's another example. Any questions for this example?
No.
Yeah, these are very basic things that you need to understand. When you see two sets multiply, you should know what it means. All right. Essentially, They just go to different places in the order pair. That's it. So that will increase the dimension from 1 to 2, right? Okay, let's look at another example. The set R2 is just R cross R, as I just said. It's called a Cartesian plane. We already know that. But why is it called a Cartesian plane? Because the Cartesian product of the set of all real numbers cross by itself. We view elements in this set as points of all the pairs x with first coordinate x and second coordinate y, with x and y both coming from real numbers. See, so that's the xy plane, or R2, So that's what we already know. Let's see what happens if you multiply a set with the empty set and see what you get. So in this example, A has 3 numbers or elements, 1, 2, 3, and B is the empty set. Then when you multiply or take the product or Cartesian product of these two sets, what do you get? You get nothing. Why? Because this cross product or not Cartesian product includes all the ordered pairs with the first entry or coordinate coming from elements in A and the second place in the ordered pair or the pairs coming from elements in set B. But if set B has no element in it, then you cannot put anything in the ordered pair in the second place. So that means you really do not have any ordered pair in this case, because you have nothing to pick up to put in, so you can not have any ordered pair. So you get an empty set. You get a set without any element, right? And similarly, if you take the Cartesian product with the B and A, B cross A, you also get the empty set for the same reason. You don't have anything to pick up from set B in the first place in ordered pairs. So there is no ordered pair, actually. So if we use the proposition we just discussed on the last page to find the cardinality of the product of AB, that's just equal to the cardinality of A times the cardinality of B, which is 3. A has 3 elements, times 0. B has no element, so its cardinality is 0. 3 times 0 is 0. So there is no element in A cross B. So that confirms our conclusion. So that's another special case. You can actually do Cartesian products of sets with more than 2 sets. For example, you can take Cartesian products of 3 sets, A, B, and C. So A cross B cross C. As I said, you just put elements of those sets in ordered pairs. So in this case, it's not a pair, but three numbers, okay, but in order. So you pick up an element number from set A, put in first place, and put the an element from B in the second place, and another element in set C in the third place. So you're gonna get the ordered triple, 3 numbers. So A belongs to set A, B belongs to set B, and C belongs to set C. And if you think about this, A, B, C are set of real numbers, so you get all times cross R, cross R, cross R. What do you get? You get X, Y, Z. Okay, if you use different notations for each entry, then you get the coordinate of a 3D space, right? So that gives you the 3D space, all the points in the 3D space. It has 3 coordinates, or 3 entries, and each coordinate is a real number, isn't it? And you can actually do more than 3 sets. You can do A cross B cross C cross D if you have 4 sets A, B, C, D, and that will give you all the numbers, 4 numbers A, B, C, D, listed in order, and so on. Or you can do Cartesian products of 5 sets, 6 sets, and so on, as many as you want. All right. So that's 3 sets. All right. Any questions about the Cartesian product of sets?
I don't have any questions.
Okay. So let's just talk about the second topic of this section, indices. All right. When you have a collection of sets, a large number of sets, for example, then it's convenient to use subscripts for the notation rather than randomly using different letters of the alphabet. You don't want to use A, B, C, D, E, F, G, and so on. You only have 26 letters. So if you have 27 sets, then you are short of the symbols for the notation of sets. So in that case, it's more convenient to use subscripts. So you can call this sets A1, A2, A3, A4, and so on, up to A27. All right. Then you can have arbitrary number of sets to index. All right. When we do that, the subscripts all come from all of the set of natural numbers. So you only use A1, A2, A3, A4. You usually don't write A0 or A-1. Although sometimes we do. In most cases, you just use natural numbers as the index. Okay. So we refer to n, the natural numbers, as the index set for this collection. Okay. So the natural number set is the index set for this collection, or for this notation. So then we have, for example, if we want to take the union of 3 sets, A1, A2, A3, these 3 sets are A1 with 3 elements, 1, 2, 4, A2 with elements -3, 1, 4, 5, 9, so that has 4 elements, and A3 has 3 elements again, 1, 6, and 10. So we can write the union here of AI, with I comes from 1 to 3. So just like the notation, the sigma notation, remember? When you write the summation of A1, A2, A3, you also write in a similar way. And the difference is just the summation becomes the union. Okay, everything else looks similar. So by that, it means the union of A1, A2, and 3. Okay, so your union A1 with A2 and with A3. So you just put all the numbers together in these three sets. So then you're going to have how many? 8 numbers. -3, 1, 2, 4, 5, 6, and 10. And actually 9 also. And that's all. You don't write the repeated elements or numbers. Okay. Or you can take the intersection of 3 sets. Okay. Just like we did for 2 sets. And this time, just change the union notation to the intersection notation. So that means A1 intersecting A2 intersecting A3. All right. So you just find the common elements from the 3 sets, and you find that there is only one common element in those 3 sets, and that's just the 1. So that's a set of one number. Okay. Pretty straight, I believe. So let's just do another example of union and intersection. So this time we have infinite many sets. So those sets are Bn with 2 elements in each set of Bn, namely n and -n. So for example, B1 will be the set of 1 and -1, B2 will be the set of 2 and -2, and B3 will be the set of 3 and -3. So n just goes from 1 to infinity. So all natural numbers. So you can write the notation like this with the union. If we take the union of all those sets, so you write union of Bn with n from 1 to infinity. That's also done, when you write the infinite sum. Remember when we did Cal 2 in series, in the chapter series, we use the same notation. So what would be the union of all those Bn's? Simple, just put all the numbers in both positive and negative. We know Hn is just the natural number. So if you put the negative sign, then this union will include all the natural numbers and the opposite of all the natural numbers. Okay, so I just wrote or listed a few elements or numbers in this set, and that's not the set of integers. It does not have 0. Okay, remember in this Bn's, you don't have 0 because n is from the natural numbers. So, but other than that, you have all the numbers from Z. So this union of Bn with n from 1 to infinity will be the set Z minus the set of element 0. Remember the difference of 2 sets, you just take off 0 from set Z. All right. So that's the union of Bn. How about the intersection of Bn? Obviously, that will be empty set. If you, for example, if you take an intersection of the set of B1 and B2, B1 is 1, -1, B2 is 2, -2. You don't have any element in common between those 2 sets. So the intersection of those sets is 0. Actually, all of those sets are disjoint. They don't have any elements in common for any two of the sets Bn. So that's about that. I guess we're gonna finish this section Wednesday. We'll try to at least. This looks like we still got quite a bit to do. So it's already 5:48. So we stop here. Any questions for this section so far? If not, I'm going to stop.